Okay then, let's get started. So talking about how we measure angles. Measuring angles, it turns out, it's going to be very similar to how we measure segments, so I'm not going to go that far into the actual process of measuring, just tell you how we come up with the definitions of these things. So we're going to be coming up with finally the definition of a degree, right? And so we can start talking about this angle being 60 degrees or 80 degrees and having it defined. And we define it in terms of the arc of a circle. So let's really quick draw a circle here and pick some, what do we call these angles? I can't remember what we call them. Angles centered at the center of the circle. Central angle, that's what we call it, thank you. So pick any central angle on the circle you want. Call the points A and B where the angle intersects the circle by the arc AB. What do you think the arc AB is of that circle?
All the points in the circle between A and B.
It's all the points on the circle between A and B. Between A and B means they're somehow on a line.
It's all the points on the interior of the angle.
All the points on the circle and the interior of the angle, and then including the points A and B. That's what we mean by the arc AB. With me? Now, what if we wanted to talk about this arc out here? If you want to talk about some arc using the exterior of an angle, you need a third point, C, and then you would call that the arc ACB, doing the order in which you would come across them if you went around. Make sense?
Yeah.
So this is referencing all the points on the circle exterior to this angle, including the points A and B. This is referencing all the points interior to the angle, including the points A and B, for any central angle. There's one exception when your central angle is a straight angle. Because what's the interior of a straight angle? It doesn't have one. So when it's a straight angle, then this is now ambiguous. And so you need to pick some other point each time, call that C, and then talk about this side, or put a D down here. And if you want to talk about that arc, then it's just ADB. So that's our definition of what we mean by an arc and the notation that we use to mark an arc. Any questions so far? Now I'm going to use some notation that's not in your book. I'm going to use notation like this, with a line above AB. What do I mean by that? That's going to mean the length of the arc. We'll be defining what exactly we mean by the length of an arc, but I'm just going to use that notation. It's not in your book. The author specifically says the length of that angle, and since we're going to be talking about lengths of these arcs over and over again, I want some notation for it. Good so far? All right. So with that, let's get started with our first theorem. Or our first definition. Let's now define exactly what we mean by arc length. So, well, our second definition. Our first definition was what we mean by the arc. So what exactly do we mean by arc length now? So if I've got some central angle here, and it goes through these 2 points A, B, you know intuitively what I mean when I say I want to talk about the length of the arc AB, right? But what exactly is that length, and how exactly can we talk about that length? And we're going to have to use a limit. You remember how we talked about the circumference last time? Let's put a pin in this for a second and come back and talk about circumference. What is the circumference of a circle? You start by inscribing some polygon in the circle, like a square, right? And calculate the perimeter of a square. And then, so that would be, well, we could start with a triangle, which would give us P3. Then we can inscribe it with a square, which would be P4. Inscribe a regular pentagon in there would be P5. Dot, dot, dot. If I inscribed a 100-sided figure inside the circle, what would that look like?
Really close to the circle.
Yeah, that would look like do. It would basically, if I could draw it, look indistinguishable from the circle. And so the perimeter of a 100-sided inscribed polygon is almost exactly the circumference of a circle. And by definition, we could keep doing this for any n-sided figure you want. We said that the circumference of the circle is by definition equal to the limit as n approaches infinity, as we add infinitely many sides, of the perimeter of these inscribed polygons. Right? So now over here, what are we going to do? If I want to get the arc length from A to B, how could I approximate that? Because I only know how to find lengths of segments. I don't know how to find the length of something curved like that.
You could inscribe a triangle on it first.
Right, so first I could just add this line, and I'll call that L1. And so, L1, that gives me an approximation. I can calculate the length of L1. L1 actually means the length of that thing, right?
Yeah.
And then instead of using one segment, I could have instead used two segments. Gone from here to there, and then from there to there. And call the length of those two segments L2. And I could have done L3 with 3 segments, and 4 segments, and 5 segments, and 6 segments, breaking it up into pieces like that. And so by definition, the arc length of AB is going to be the limit as n approaches infinity of these lengths. Make sense? Now I said when we break it up into 1 pieces, 2 pieces, 3 pieces, 4 pieces, 5 pieces, etc., you might wonder, how do I break this up into 3 pieces, for example? Breaking it up into 2 pieces, that's easy, right? How can I break it up into 3 even pieces? That's kind of hard. What about breaking it up into 4 pieces? If you know how to break it up into 2 pieces, can you break it up into 4 pieces?
Yeah.
Yeah, just find the midpoint on this segment, take its perpendicular bisector where it goes through, find the midpoint on that, and then that breaks up into 4 pieces. And then breaking it up into 8 pieces and 16 pieces and 32 pieces, right? And it turns out you can use that as your definition if you want. So you can get away from having to think about breaking it into 3 pieces. You can skip straight to 4. You can skip, you don't have to think about how I break up into 5 pieces, 6 pieces, 7 pieces. You can go straight to 8.
Yeah.
You don't have to think how I break up into 9, 10, 11, 12, 13, 14, 15 pieces. You can go straight to 16. And it still works. So that's the way the author defines it. It's counting by 2s, and that's the reason that he does it. Multiples of 2. So you don't have to overthink about how you would break it up like that. But I'm just going to say break it up into 3 pieces, and we'll pretend that we know how to do that from here on out. So, slight way that I differ from the author if you're following the book. Any questions so far? So the arc length is break into 1 segment, calculate the length, then 2 segments, calculate the length, then 3, then 4, then 5, then 6, and the limit as n approaches infinity. As we break it up into that many segments between A and B, calculating the length of all those segments gives me what we mean by the length of the arc. Good? Okay. Our first theorem, 12.1. If in a circle 2 central angles are congruent, they subtend arcs of equal length. So theorem 12.1. If 2 angles, yeah, 2 central angles, if 2 central angles on a circle are congruent, comma, are congruent, comma, then their what must be equal? If the 2 angles are congruent, then what?
Their arcs.
Yeah, their arc lengths must be congruent, or must be equal. Their arc lengths are equal. All right, we'll mostly just rely on a picture for this. We can write out the actual proof if you want the actual proof. So let's really quick get a circle here. And I'm drawing 2 angles on the circle that are congruent to each other. So there's a point A, here's a point B, our center point here is O, and then we've got some other angle over here. Using point C and D. And all I know is that this angle is congruent to that angle. What am I trying to argue? I'm trying to argue that the length of the arc from A to B is equal to the length of the arc from C to D. Right? Okay. So how could we argue that? First off, let's see what happens when, let's let L1 here be the length that connects these two. I'll call that one L1. And then I'll call this one L1 prime. How does L1 compare to L1 prime?
Length of same length group.
How do you know?
Because CL and DL are the same length as AL and BL.
What is the distance from O to A here?
The radius.
It's the radius of the circle. What is the distance from O to B here?
Radius.
Radius of the circle. This distance, radius of the circle. This distance, radius of the circle.
So the triangles are grouped.
And so these two triangles are congruent by side angle side. And so the length from A to B is equal to the length from C to D. So I know that L1 is equal to L1 prime. What if I broke it into two pieces now? Where we went right through the middle. So if I broke it into two pieces, now pretend that that was right smack in the middle. So this segment is congruent to that segment. Now that splits into these two triangles, and that splits this into these two triangles. Well, now this angle is exactly half of this angle. My picture is lying. And this angle is exactly half of this angle. This is still the radius for both of them. And all four of those triangles are all congruent to each other. Right? And so L2, which is the length of this segment plus the length of this segment, is equal to L2 prime, which would be the length of this segment plus the length of this segment. That's L2 prime. This is L2. Right? And if I broke it into three even pieces, what happens?
Same thing.
Same thing. And so I also get that L3 is equal to L3 prime. Dot, dot, dot. And in general, Ln, if I break it into m pieces, is going to be equal to Lm prime. You see that?
And we know because the triangles will be...
Yeah, because it keeps making the triangles congruent. Every time you break it up into that many pieces, you make that many equal pieces, you make that many congruent triangles. All of them congruent to each other. Make sense?
Yeah.
Okay, so then what is A, B's arc length measured at? What is the distance from A to B? By definition, what is that?
It's the limit as
It's the limit as n approaches infinity of L sub n. But what is L sub n equal to?
L sub n prime.
This sequence is the exact same as L sub n prime sequence. So this is equal to the limit as n approaches infinity of L sub n prime. Which that is equal to, by definition, arc CD. Arc CD's length. You see all that? Any questions so far?
Do they have to be central angles?
Yes. Only talking about central angles here. They're both central angles. That were congruent to each other. If they weren't central angles, then these distances wouldn't have been the same as these distances. It had to do with the fact that those were radii. So we definitely use the fact that these are central angles, and this is not something that's in general true. Right? Okay, so there's theorem 12.1. Theorem 12.2 is not one that we're proving, but theorem 12.2 states that, let's draw a circle here. So in getting the arc length between A and B, by definition, we decided to break it up into even pieces. We break it up into 2 even pieces, and then we could go to 4 even pieces, and 8 even pieces, 16 even pieces, right? And to get the arc length, Theorem 12.2 says we don't have to keep breaking these up into even pieces as we go. All that matters is the pieces that we break it up into get arbitrarily small. In other words, to get the arc length from A to B, I could consistently cut it at a ratio of 2 to 1. So I could come here and make my first point that I split it into. So first, L1 would be going straight from A to B. L1's still the same, right? My next one, I could add my point down here. So that's 2/3 and that's 1/3. And now that would be my L2 going from there to there. And then next, I could break each segment into 2/3 segments. So come down 2/3, put that point in, come down 2/3, put that point in. Right? And use those points. And then I could break all those into 2/3 segments. So come down 2/3 away for that, come down 2/3 away for that, come down 2/3 away for that, come down 2/3 away for that. And use those points. And if I keep doing this process, eventually I break the entire thing up into arbitrarily small segments. As long as I keep breaking them down smaller and smaller, it doesn't matter how I break them down, it just matters that I am consistently breaking them down. So that is a theorem of real analysis, of calculus basically. We won't be proving that in this class. That's a somewhat difficult one to do. And for those of you from calculus, you might remember that it's very similar to how we talk about a Riemann sum. The biggest gap has to go to 0. Same concept. Okay, so that's theorem 12.2. It's not one that he proves, it's one that he just states. Okay, so theorem 12.3 is, if arc AB and BC are adjacent to each other, then the sum of the measure is equal to the measure of the sum. So theorem 12.3, and it is essentially that the measure of the sum equals the sum of the measure. That's the mnemonic that we use to remember it. And so what is it saying? It's saying we have 2 central angles that are adjacent to each other. Here's a point A, here's a point B, here's a point C, with O right here. And we're trying to argue that the length of arc AC is equal to the length of arc AB plus the length of arc BC. That's the argument we're trying to make here. With me so far?
Yeah.
Now, we'll come up with our sequence for AB here. We'll say that the limit, we'll say that AB's arc length is equal to the limit as n approaches infinity of, we'll use L sub n for that one. So here's L1. Right? And for this arc, BC, we'll say it is equal to the limit as n approaches infinity of L sub n prime. So here is L1 prime. Good? Let me draw L2 really quick for both these. Here's L2 and L2 prime. What would those look like? Those would look like going like this, and then like this, and going like this, and then like this. You see it? Now notice that the total arc from A to C, we are not breaking it up into equal pieces. The pieces that we have up here when we get to 2 are bigger than the pieces that we use down here when we get to 2.
Yeah.
With me? But our previous theorem says it doesn't matter as long as your biggest pieces are always going to 0. And if we keep doing this process indefinitely, are all our segments becoming 0 in length?
Yeah.
Yeah, so that doesn't matter. And so we can use this sequence then to calculate the arc length from A to C. So let's finally write that now. So the arc length from A to C, we're going to say is equal to the limit as n approaches infinity of the sequence that we get by adding this with this. So it's what we get when we take Ln and we add it with Ln prime. And by theorem 12(2), the one that we skipped proving, this is a valid way to do it even though we're not breaking those up into even-sized pieces. Now, going clear back to our limit rules, one of our limit rules is that the limit of a sum is the sum of the limits. So this is equal to the limit as n approaches infinity of L sub n plus a limit as n approaches infinity of L sub n prime. But what is the limit as n approaches infinity of L sub n? What was the limit of this sequence equal to? That is the arc length from A to B. That's exactly what it is. So that is AB's arc's length plus, and this one is just exactly what we mean by the arc length of BC. So BC's arc's length. And so there it is. The arc length from A to C is equal to the arc length from A to B plus the arc length from B to C. And ultimately it just relies on the fact that the limit of a sum is the sum of the limits. That's the only real logic that underlies that argument. Well, I guess in the previous here. Any questions on that? All right. So that's the limit stuff. I know you guys aren't as comfortable with that stuff. Let's get now into the more geometric type proofs with this, more picture-oriented ones. So our next theorem is if in a circle one central angle is greater than another central angle, then the greater angle subtends the longer arc. So theorem 12.4. Theorem 12.4 is bigger angle implies bigger arc. Draw it that way. So let's draw out our picture for this. So we've got two central angles on the same circle. Here's angle AB. Here's angle CD. So here's AB. Here's O. Here's C and D. And what do we know? We know that this angle, I'll name this angle alpha just so that we can reference it. Alpha is this angle, and we'll call this angle right here beta. Just so that we have names for these things in case it's useful to talk about. So what do I know? I know alpha is larger than beta. What does it mean for one angle to be larger than another angle?
You can fit the small angle in the interior of the bearing.
Well, it's not just that we can fit the smaller angle in the interior somewhere. It's a very special way. It had a precise definition. What does it mean for one angle to be smaller than the other angle?
That like if you put a ray that's
There exists some ray in the interior I can draw such that it makes a congruent angle with one of the sides.
and there's extra. There's like
Well, in the interior of the angle is exactly what it is. Not on the angle, in the interior. So that's going to imply that there's extra. But that's exactly what it meant for one angle to be smaller than another. So that means that I can construct, maybe naming these won't help. I can construct some ray in the interior here. I'm guaranteed this ray exists. Such that this angle is congruent to that angle. Now, what am I trying to argue? Let's really quick call this the point E.
That the arc length is bigger.
arc length is bigger.
I'm trying to argue, in our picture, I'm trying to argue AB's arc length is greater than CD's arc length.
Well, we know that by
Well, you
theorem
can just
12.3,
say since EB's arc length is congruent to CD's, then
Their arc lengths are equal. Remember, those are numbers.
or yeah, they're the same. Yeah, and then you add AE makes it well.
You've got the idea, so let's really quick do this. So I know that AB's arc length is equal to what?
it's equal to arc length of AE plus EB.
AE plus EB. How do I know that?
Theorem 12.3.
Because E is between A and B on the circle.
Well, we know that. just by this previous theorem.
Oh, well, that too. Yeah.
The measure of the sum of the angles is equal to the sum of the measure of the angles. Good? Okay. Now I know that this is equal to
CD. The arc length.
AE is still there.
Plus.
Plus, instead of EB, we can use CD
Because they're
arc
equal.
length because those numbers are equal. Right?
Yeah.
Which means that this is equal to the sum of those two numbers. So it's for sure greater than just this number by itself. If I get rid of that, I made the number smaller. There's no such thing as a negative distance.
Well, it could be 0.
No, it can't be 0. How do I know it can't be 0? And that is a good point. How do I know that AE cannot be 0?
Because then EB
Because then
would
they-
be on the line of.
Because then E wouldn't be in an interior point. So I'm guaranteed that this angle is an angle. Has some value to it, which means that this distance has some value to it. Good? It's good to think through those kinds of technicalities. So the arc length of AB is equal to that, is greater than just CD by itself.
Did you see that?
Alexander,
Here's your test.
thank you so much. You guys knew it was a test day, right? Okay. So any questions on that one?
Well, that makes sense.
Okay, let's move on to our next theorem. That was 12.4. All right, 12.5, the converse. If one arc of a circle is longer than a second arc of the circle, the longer arc is subtended by the greater angle. So this one said, bigger angle implies bigger arc. Our next one, we're going to prove bigger arc implies bigger angle. Make sense?
Yeah.
Let's shove the camera. Okay, so theorem 12.5 essentially says bigger arc implies bigger angle. Okay, so let's set up our picture here. Help us think about it. A, B, C, D. Here's A, here's B, here's C, here's D. I'll call this angle angle alpha, and I'll call this angle angle beta. Understand the picture so far?
Yeah.
Now what we know is that arc length AB is greater than arc length CD. That we know for sure. So, observe. We know that AB's arc length is greater than CD's arc length. Okay. What are we trying to argue?
I'm trying to argue that AB is greater than CD.
I'm trying to argue alpha is larger than beta.
Yeah.
That's what we're trying to get to. With me?
Yeah.
Okay. So how do I say alpha is larger than beta?
You have to show that there's a ray in AB that contains.
We could do it that way, but
Can you take the contrapositive of that statement?
you could take the contrapositive. We're just going to do proof by contradiction. That's probably the easiest way to go about this. But contrapositive is pretty close to the same. Okay, so 2, assume, by way of contradiction, that alpha is not greater than beta. So if alpha is not greater than beta, what must alpha be?
Congruent, that's one.
If alpha is not greater than beta, either alpha is congruent to beta or alpha is smaller than beta. Okay. What happens? If alpha is kind of just a scratch proof. Alpha congruent to beta, what would that imply? If alpha were congruent to beta, what would I know about arc AB and arc CD?
They're the same.
That would mean that they're the same length. We already proved that over here. If two central angles are congruent to each other, then their arcs are equal to each other, their arc lengths. So if alpha were congruent to beta, then I would get that AB's arc length is equal to CD's arc length. How do I know that's impossible?
Because we were given that.
Because we're given that AB's arc length is bigger than CD's arc length. So that can't be the case. Whoops, contradiction. What happens if alpha is instead smaller than beta? What does that give us?
That the
AB's arc length is
smaller than CD's arc length.
We already proved bigger angle means bigger arc length. So if beta is bigger than alpha, what do I know? Beta's arc length is bigger than alpha's arc length. So that would give me that the arc length for alpha is less than the arc length for beta. Contradiction, because I know that alpha's arc length is bigger than beta's arc length.
yeah, from the previous theorem here. Okay.
So if the arc length isn't equal, and the arc length and AB's arc length isn't less than CD's arc length, what do I know?
It's gotta be greater.
Oh wait, sorry. That's not what we did. So we assumed by way of contradiction that alpha was not greater than beta. In either case, we got a contradiction. Therefore, alpha must be greater than beta. Because if alpha wasn't greater than beta, we'd either have this as the case, which is impossible, or this is the case, which is impossible. So therefore, alpha is greater than beta. Kind of scratching out the proof. That idea there makes sense?
Yeah.
Yeah.
You wrote that.
That is-
by the way.
I don't know how you count.
I do 1,
You're doing it wrong.
3, 4.
Okay. Anything else? Looks good?
Yeah.
All right. Next one, theorem, we're on 12.6.
Yeah.
The central angle of a circle are congruent if and only if they subtend arcs of equal length. Okay, so theorem 12.6 is saying same angles if and only if same arcs.
Central angles, right?
Yeah, central angles, always on the same picture. It says precisely that the central angles are congruent if and only if the angles, arcs, lengths are equal to each other. Okay? So let's scribble out our picture. So I've got two angles here. That is supposed to be the center of the circle. Here's alpha, we'll just piggyback off of this picture. So, piggyback off of this picture as we think about this. Let's go the forward direction first. So we need to show that if the angles are congruent, then the arc lengths are equal. That's the first direction. How do we know that?
We proved that every.
We already proved that. That was our very first theorem. If two central angles on a circle are congruent, then their arc lengths are equal. So this first direction is already just theorem 12.1. So we already did that way. Okay, so let's think about this the other way. I want to prove if they have the same arcs, then they have the same angles. So this time, going this way, let's assume that they have the same arcs. Assume that, we're going to piggyback on this picture. So let's assume that the arc length of AB is equal to the arc length of CD. And I'm trying to prove that alpha then is congruent to beta. So just to make our picture make sense, let's get a picture that actually represents the scenario we're talking about. So AB, alpha, beta. If I know that AB's arc length is equal to CD's arc length, I'm trying to prove that alpha is congruent to beta. Right? That's what I'm trying to prove. Now, how can we prove this? Big hint, look at the last theorem we proved. Assume,
We could do, yeah, the.
by way of contradiction, that angle alpha is not congruent to angle beta. All right, if alpha is not congruent to beta, then what do we get?
So less than or greater than.
That's less than-
Yeah, then alpha either has to be smaller than beta or alpha has to be greater than beta.
Yeah.
So, if I get that angle alpha is less than angle beta, what does that give me? If angle alpha is less than angle beta, what do we know?
That angle beta's arc length is bigger.
Yeah, then angle beta's arc length is bigger. Bigger angles have bigger arc lengths.
Yeah.
So that gives me that. So if alpha is smaller, then that gives me that AB's arc length is less than CD's arc length. Contradiction, because we know that they're equal. 4. Well, not 4. We'll just keep going. And if angle alpha were instead greater than angle beta, what do we get?
The angle alpha.
That AB's arc length is greater than CD's arc length. Again, contradiction. Right?
Yeah.
So therefore, we get that angle alpha is congruent to angle beta. So, two central angles of the same circle, if they subtend the same arc lengths, then they're congruent, and if they're congruent, then they subtend the same arc lengths. And if one's bigger than the other, it has a bigger arc length, and if one's smaller than the other, it has a smaller arc length. All the things we know and love and would expect just from the picture, now we can assume. Make sense? All right. What is our next one? 12.7. If A, B, and A prime, B prime are arcs on two circles of radii r and r prime respectively, then they subtend, or respectively, and are subtended by congruent angles, then the arc lengths are proportional to their radii. Okay. So, this one we're crossing circles now and comparing across circles. So this time, what theorem was this?
Also.
Theorem 12.7. And essentially what we're trying to prove is, how can I scribble? Let's write the picture and then what we're trying to prove I'll write in terms of our picture. So I've got let me make that slightly bigger. So we can, this would be our smaller circle. Okay, so I've got one circle here. It has radius r. And we've got an arc using the points A, B, O. Over here, this is R prime using point O prime. Here's point B prime. Here's point A prime. With me? Trying to show that angle BOA congruent to angle B prime, O prime, A prime implies what?
That the arc length is proportional.
Yeah, the arc lengths are proportional to the radii. How do I write that in mathematical notation? What does it mean for them to be proportional?
R over R prime is equal to the arc length square root of.
Yeah, so I'm trying to show that AB's arc length over A prime B prime's arc length, is equal to r over r prime. They're proportional.
You could also write AB over R is the same as A prime B prime over R prime.
Yeah. But here's the way that we're going to want to demonstrate it. Okay. Now, if we're using proportionalities, what types of triangles am I looking for? Similar triangles. So first off, let's think about the arc length here of AB. How do we get its arc length? Well, first, I'm going to use one segment connecting those points, and its length we call L1. And then I use two segments connecting those points, and that's what we mean by L2, etc., right? And over here, we're going to do the same thing except for with like L1 prime and L2 prime. So let's start out by drawing the L1 case and see what we notice. So here's L1, here's L1 prime, right?
Yep.
How does L1 and L1 prime, what do we know about the relationships between these things? First off, I know that this angle is congruent to this angle. Let's not forget that fact. This angle and this angle are congruent. Okay, so we know that.
Have to be proportional. Have to be similar.
Does this triangle have to be similar to this triangle?
Yes.
How do you know?
Because they have two sides the same length.
So this is
Or that's a
these are both isosceles triangles, right?
yes.
And so the base angles have to be congruent. And the angle sum of this is a straight angle, and the angle sum of that is a straight angle.
Yeah.
That's how to make it appeal to your intuition. We've in fact already proved this fact. But make it re-appeal to your intuition. This angle plus two of those is 180 degrees. This angle plus two of those is 180 degrees.
So the two
Since
sides-
these ones are the same, then those ones also have to be the same. That's just trying to make it appeal to your intuition real quick.
Right.
But we already did this with inscribing regular polygons inside these shapes.
So if we know that they have three angles from here, we know this one.
Right. So these two triangles have to be similar to each other. So how does L1, what do I know about L1 and L1 prime? What does that give me since these are similar triangles? So similar triangles have all their angles congruent and
Other sides proportional.
all their sides proportional. So L1 over L1 prime is equal to what?
R and R prime.
Yeah, this over this is equal to that over that is equal to this over this. So it's equal to R over R prime. You with me?
Yeah.
Let's look at the case of L2. If we split this up into two pieces,
Oh, I see.
so now it comes like that, then down, that's L2. And L2 prime comes up and down like that, that's L2 prime. Where it perfectly bisects the angle. You with me?
Yeah.
What do I know about this triangle and this triangle and this triangle and this triangle? They're all going to be similar to each other. Same type of argument. I already know that angle is the same as that angle. I already know that angle is the same as that angle.
And because it bisects, you know those two angles too.
Right. A bunch of different ways that we could try and make this type of argument. So in either case, you see how all these triangles are all similar to each other? It's kind of exactly like what we were doing over there, except for in that case, it was all the triangles are always congruent to each other. In this case, it's when we break it up, they're still similar to each other. And so I get, once again, that L2 over L2 prime is equal to R over R prime. Right? And if I broke it up into n triangles, and broke that up into n triangles, all the triangles would still all be similar to each other. Make sense? So then, adding up all the lengths, we still maintain the proportionality. And so, now let's just write it out. So I know that AB's arc length over A prime B prime's arc length is equal to the limit. I'm going to stop writing as n approaches infinity. That's always the limit that we're taking. So that's equal to the limit as n approaches infinity of L sub n over the limit as n approaches infinity of L sub n prime. Now, going back to our limit rules, the limit of a quotient is a quotient of the limit as long as the denominator is not 0. Is our breaking up of lengths here ever 0? No. So this is the same thing as the limit as n approaches infinity of Ln over Ln prime. But Ln over Ln prime is equal to what? R over R prime. So this is the limit of R over R prime. What's R? Your radius. How does your radius change as we break this up into more and more pieces? It doesn't. How does our radius over here change as we break R up into more, or break this up into more and more pieces? It doesn't. So R and R prime are constants. What's the limit of a constant? It's the constant. So this is just equal to R over R prime. Good. And so the side, the arc, the lengths of the arc are proportional to the radii.
Okay, I see that.
Good? Okay. 12.8, we are not proving. But what does 12.8 say? It says, pick any arc length that isn't the circumference. It's between 0 and the circumference. So pick any arc length, start wherever you want, A. Pick any arc length that's less than the circumference, which gives you to the point B. It says that there is a interior angle corresponding to that arc length. So as long as your arc length is less than the circumference, you can find some interior angle corresponding to that arc length.
Why do you not prove that?
This, again, is getting into real analysis, because it's basically saying that, I don't know if we've even used the terminology dense yet. We did in topology, but I don't know if we've used it here. But it's the idea that this circumference of the circle is dense, that you won't hit a hole.
I see.
That's the idea.
Dense or compact?
Dense. No holes. That the topological space of the circle is connected. No holes. Okay, so that's what it's getting at, which is as intuitive and as obvious as that seems, the proof of it is not trivial.
That's so...
And it goes back to one of our basic one of our last postulates. One of our last postulates, it was called the completeness postulate. And it was just a postulate for the real number line. And we basically said, pick any number you want. There is a segment whose length is that number.
We can't use that here?
You would use it here.
Oh, we have that postulate, so I can't prove it.
It's possible to prove.
Well, what
It's
can-
not trivial to prove.
Can we prove it with all the tools that we have in our geometry?
Yes, you have everything that you need in your geometry, because we have in our geometry everything we need from calculus. It's just not obvious how this completeness axiom is the same as the one that you use in calculus. The completeness axiom that you use in calculus, see, this one says, pick any real number, there's a length that corresponds to it. In calculus, what is it? It's every non-empty set of numbers bounded from above has a least upper bound. That's the one you use in calculus. And how those two are connected wouldn't even begin to approach your intuition. It's just so strange.
Yeah.
But there you are, that's exactly what it is, and it turns out that fact is what makes the real number lines dense, gives us this fact, and then you use this fact to come and argue it for on a curve. But calculus, it's much easier to talk about curves in calculus than it is just relying on the geometry.
How would we go about doing that? Find that curve.
We will be doing that in calculus tomorrow. Talk about how we measure curves and the lengths of curves.
How would we do that?
I mean, it's intuitively, you already have the idea. It's exactly what we're doing here. Break it up into a bunch of segments, and then integrate the lengths of all those segments. Do the infinite sum of the segments as they get arbitrarily small. So it's an integral.
That's not hard.
Well, when you're already comfortable with integrals,
Well, we don't need.
but coming up with a purely geometric argument is more difficult because you have to use limits. You're more comfortable with it because you see that's an infinite sum, and so it's using an integral.
I see. I follow.
It's okay. I mean, you eventually do get to cover it in calculus. It's just when's the right time to do that deep dive is always a question.
There's so much calculus in my geometry.
Yes, it's because there's a lot of concepts that you need calculus to talk about precisely.
It's funny.
It's bothering.
That's why I always like to teach real analysis
Yeah.
to high school kids, which people say you shouldn't do too much. Okay, so now we're finally going to get to degree and the definition of a degree using
We do degrees or radians first?
degrees. Let's give you what you know, you love, your favorite thing in the whole world, degrees. What is a degree?
It's 1/360th of a circle.
What does that mean? How do I take 1/360th of a circle?
360. It means you divide the circle into 360 points so that the arc length is lacking on it.
Yeah, so we come over here and I mark off A and B here,
Such that
and I do it such that this arc length is equal to what?
1/360th of the circumference.
Let's say that this has radius r. So if I want this to be 1 degree, by definition, that's a central angle that corresponds to an arc that is 1/360th of the circumference.
Yeah.
So the arc here is going to be 1/360th of the circumference, or in other words, it's going to, what's circumference over 360, right? Which is equal to, what's the circumference?
2 pi times radius.
2 pi times the radius over 360. You can cancel out 360 and 2 and get pi r over 180. That is our definition of a degree. It is the central angle that corresponds to an arc length of pi times the radius divided by 180.
Makes sense.
What a stupid definition. Where on earth did this come from?
It's really nice to use.
Why do we divide the circle up into 360 pieces?
Space 12. So it's just easy to do.
So this goes all the way back to the ancient Sumerians. And the ancient Sumerians had a base 60 counting system. We have a base 10 counting system. They used a base 60 counting system. Now, notice in our base 10 system, there's numbers when you're performing arithmetic that you like to use. And the numbers that you are happy to see show up are numbers like 1, 2, 5, and 10.
Yeah.
If I say 1,000 divided by 10,
Better.
it's 100. You hardly even had to think about it, right?
Yeah.
Or even if I said 1,000 divided by 5, it's still pretty easy, 200.
Better. Yeah.
Or 200 times 5, or 200 divided by 2. You like it when we're using these types of numbers. 3, oh, we don't like 3, right?
Yeah.
10 divided by 3, get out of here. Don't even ask me, I don't want to think about it. The reason that's so easy for us to do arithmetic in our head, using 1, 2, 5, and 10, is because those are the factors of the number 10.
Right.
And so we get used to doing arithmetic with that. In a base 60 counting system, what are its factors? Well, obviously 1, but 2 goes into 60. 3 goes into 60. 4 goes into 60. 5 goes into 60. 6 goes into 60. And so all these early numbers all go into 60 evenly. And so it was very easy for them to do arithmetic in their heads involving these types of numbers using a base 60 counting system.
Makes sense.
Very divisible. So that's one of the reasons. And then for the calendar that they would use, their calendar had 360 days in the calendar. Not 365, but 360 days. And then they would just add 5 days at the end just to resync their calendar up with the sun. They used a lunar calendar. You understand the difference between a lunar calendar and a solar calendar?
Yeah.
The moon goes through its cycle once every, how long does it take a moon to go through its cycle?
28 days. 30 days.
29 and a half days. Almost 30 days. And so they had a month for each lunar cycle. You have 12 lunar cycles, and then to keep in sync with the sun, you had 5 days at the end. So their calendar had 360 days split across 12 months, 30 days per month, nice and simple. When the Romans came along, they did all sorts of stuff. They added the days to the months to make so that your year had 365 days when you get to the Julian calendar.
Yeah.
But they also just stuck it in all sorts of places and switched all sorts of things up. Like the Romans, their early calendar before Julius Caesar came along, started with March. That was their first month.
That actually makes sense.
So they had March, they had April, they had May, and then July was like Quintilis, and then August was like Sextilis, and then they had September, the 7th month, October, the 8th month, November, the 9th month, December, the 10th month, and then January, the 11th month, and February, the 12th month.
Why don't we have it like?
Well, when Julius Caesar came along and redid their calendar, he changed it to start in January. Line it up with the sun. It's trying to make the year start with
The sun.
the solstice,
Right.
right? When does winter start?
One second, December.
Like December, late December.
Yeah.
And so it's trying to get closer to the solstice.
I see.
When winter actually starts. Like your first 3 months are winter, followed by 3 months of spring, followed by 3 months of summer, followed by 3 months of fall. Repeat.
Why not start in spring?
Well, you see, March was kind of closer to doing that idea, but that's when they were using the lunar calendar. And then a solar calendar is basing it off of the sun rather than by the moon. Well, that's why months essentially have 30 days in them. That's how long it takes the moon to go through the cycle. And why does a year broken into 12 months? That's how many lunar cycles you can get in a year, basically. And then why do we break months down into weeks? Well, they're counting the 4 phases of the moon, one for each week. So lunar calendar largely orients all that stuff. Anyway, so that's a little bit of some history about calendars and how we measure time and where this 360 comes from. Completely arbitrary. It's garbage. We hate it. But we adopted it, and so it's what's used everywhere. It's kind of like using feet and miles. Bunch of nonsense. Right? Got a foot.
It's a lot.
We need something longer than a feet. Oh yeah, let's take 3 of them. We'll call that thing a yard. Well, if we want to talk about really long distances, how many yards should that be? Well, forget yards. We'll use 5,280 feet, of course.
It's better than that. At least it's divisible.
Well, it is better than what we did with feet, yards, and stuff. But anyway, so yes, we break the circle up into 360 degrees, and then 360 degrees, each degree is broken up into, what's 1/60 of a degree?
1/63?
Yeah,
It's
called a minute. It's another unit. Yes, a minute.
Yeah.
And then 1/60th of a minute we call a second.
Yeah.
And it's also why when we measure time, we also measure time in terms of
Is it arc minute? Is that what it's called? Or is it just a minute?
just a minute and just a second.
Really?
Yep.
I thought it was arc second.
There may be authors that often put that qualifier on there to make sure you understand we are talking about an angle measure, not
A unit of time.
a unit of time. That could very well be the case. But no, it's just called minutes and seconds. Anyway, so that's where all this comes from. Let's derive a couple formulas really quick. So this was the arc length that corresponds to an angle of 1 degree.
Yeah.
What about if I want to get tricky with you, and I want to talk about now an angle of 2 degrees, not drawn to scale, obviously. What is the arc length now for an angle of 2 degrees?
It's 2 pi r.
It's 2 times as big as this.
Yeah.
So the length that this would be for 2 is equal to 2 times pi r over 180.
Which is 2 pi r 180.
Right? And what if I did 10 degrees here?
It's just
What would this length be out?
10 times out.
It would just be 10 times this number. Okay? Now, commonly, when we just have an arbitrary variable now, we use theta. So now let's say that angle is theta. What's theta? It's just a variable representing an angle. So if this is theta, what's the arc length for the angle theta?
It's theta pi r over 180.
It's just theta times pi r over 180. So here's a formula you would use. So if I gave you a problem, I said I'm over here, I'm walking in some circular garden, here's a path in the garden. We know that the radius of the garden is 7 meters. And I start here and I walk around here 135 degrees. How far do I walk? Or in other words, what's that length?
135 pi.
And so that length would equal 135 times pi times what's our radius? 7 meters, all over 180. 135 over 180 is obviously 3/4, right? And so you got 3 times 7 is 21. 21 pi over 4 meters. That's how far you walk.
That's useful.
Make sense? Now let's imagine I told you the reverse. I said instead that I walked up here and I measured it very carefully and I walked exactly 21 pi over 4 meters, right? And instead I wanted you to figure out the angle I must have walked. How would we find that? We just need to solve for theta over here. So starting with this formula, take this formula and multiply both sides by the same number. If I take an equation, I multiply both sides by the same number. I didn't change the equation. So I'm going to take this equation. L is equal to theta times pi r over 180. And I'm going to multiply this side by 180 over pi r. And I'm going to multiply this side by 180 over pi r. And what's going to happen?
Pi hours.
That 180 crosses with that 180, those pi r's cross out with that pi r's. And I get our equation, theta here, is equal to 180 over pi r times L. Make sense?
But we know L is 21 pi over 4. Trying to solve theta.
Right, and so now I could take that, I could plug it in right there, and we could rework out what theta would be. So now let's really quick work out what theta would be. So it would be L, which is 21 pi over 4, times 180 over pi times, what was our R? 7. So this is equal to, the 4 cancels with the 180. How many times does 4 go into 180? Come on.
45.
45 times, right? 180 is 4 45-degree angles. Okay. 7 crosses out with the 21 leaving. Three. Oh, come on, guys. I'm going to send you back down to Masada. Tell them to send you back when you're good and ready. And then finally, the pi crosses out with the pi, and we're left with 3 times 45 is 135, and it's degrees. Woo! You did it. Confetti. Okay. That is using, you're going to want to know those formulas, by the way. Put those on your note card for your next test. But that is using this crazy thing we call a degree. Absolutely asinine. Now let's go to sanity world.
Radians.
Of course. Yes, sanity land. How we talk about these things when we decide that we're not just going to pick arbitrary numbers and actually try and make the math come out nice. Because again, it doesn't matter what unit you use in talking about an angle, just like it doesn't matter what unit you use in talking about distance.
Right.
It doesn't matter if I use feet to measure the length of this classroom or if I use meters to measure the length of this classroom. It changes the number that comes out, but that's not really important. So I'm going to introduce you to a radian. And a radian is going to change how we do these calculations. So a radian now, the way that if you go into more advanced math, everyone measures angles in terms of radians. No one uses degrees. So using radians, what is a radian? Rather than saying, let's have our unit correspond to 1/360th of the circle's arc length, a radian says, let's take our circle, and we'll make our unit, if this is r, we'll make our unit 1 radian now, corresponds to the angle whose arc length is the radius. That's what a radian is. It's the angle whose arc length corresponds to exactly 1 radius. Rather than 1/360th of the circle, let's just do 1 radius.
Yeah.
Now, I guess we didn't say very much about this, but 1 degree on one circle, that angle is going to be congruent to 1 degree on another circle, is congruent to 1 degree on another circle. How do we know that? Well, the degree is defined in terms of the arc length, and we proved over here in 12.7 that the arc length is always proportional to the radii. So it's consistent across circles. It's always going to be proportional. So on a big circle, if 1 degree corresponds to 1/360th of its arc length, then on a small circle, you're going to get the same thing. Same with on a big circle here. 1 radian will always correspond to an arc length of 1 radius. It doesn't matter how big you draw the circle. If I make the circle bigger, I made the radius bigger. And so I made the arc length bigger. And it will always stay proportional. Make sense? Okay. So now, we're going to try and come up with similar formulas here. You with me? Okay, so let's first think about how many radians are there in a circle. Maybe help get some intuition for these things really quick.
2 pi.
So 360 degrees, or over here we'll do degrees and we'll compare to radians since you're already comfortable with degrees. And we'll make a little table here. So what is 360 degrees in terms of radians? How many radiuses are there going around the circle?
2 times pi. That's your circumference.
If I start right here and I walk 1 radius, that gets me to here. If I walk another radius, that gets me to like right there. If I walk 3 radiuses, that gets me to right there. If I walk 3.14159 exactly pi radiuses, that gets me exactly halfway around the circle.
Yeah.
If I go all the way around the circle, that means I went the circumference. What's the circumference of a circle?
2 pi.
2
R.
pi r. Right? That's the circumference of a circle. 2 pi radiuses. So how many radiuses do I walk going all the way around the circle? How many radiuses do I go?
2 pi.
2 pi radiuses. 1 radius gets me there, or there, 2 there, 3 there, 4 here, 5 here, 6 here, 6.28, exactly 2 pi gets me right there if I walk exactly 2 pi radiuses. So going all the way around the circle, how many radiuses did I go? 2 pi. So what is a measure of the angle going all the way around the circle?
2 pi.
2 pi. That's how many radians there are in a circle, because that's how many radiuses it takes to go around the circle. How many 360ths of a circle are there in a circle? 360. That's why there's 360 degrees in a circle. How many radiuses are there in a circle?
2 pi.
2 pi. That's why there's 2 pi radians in a circle.
Gotcha.
Make sense? So what if I went exactly half the circle?
Then it would
180 degrees. What's exactly half of it?
pi.
Just pi.
How do
So
we know
pi
that-
radians is 180 degrees.
How do we know that pi is the number we use for those rounds?
We derived the
Just drag it here.
Pi, by definition,
Uh,
is circumference over diameter, or in other words, is circumference over 2 radius. Move that over there and you get circumference equals 2 pi r. So that's the exact definition of pi, and we proved, I think it's last time, that this ratio is the same for any circle.
Yeah, we did.
So pi is a constant, doesn't change circle to circle.
Okay, yeah.
Okay, 90 degrees. Sorry, let's remember that circumference is equal to 2 pi r. So 90 degrees, what portion of a circle is 90 degrees?
1/4.
1/4 the circle. So what's 1/4
Pi.
the circle?
Half on pi?
Pi halves. Well, if we went 45 degrees,
Pi 4.
just pi fourths,
Okay.
etc.
So it's just divided by 2.
Well, that's just half of that, that's just half of that. I'm intentionally counting down that way. Let's do another one just to break the pattern. 60 degrees. What portion of the circle is 60 degrees? 1/6.
Yeah.
How many times does 60 go into 360? 6 times. So what's 1/6 of that?
Pi 3.
It's 2 pi over 6. Cancel out the 2 top and bottom, or it's pi thirds. Right?
Yeah.
It's very hard to get comfortable with new units to begin with. You hate it, you're going to resent it. It's a billion times better. Why is it a billion times better? Let's find out. So now, that is 1 radian, its arc length is r, right? What would be my arc length if we had 2 radians here? Now what's the arc length?
2R.
Just 2r. And in general, if I tell you that this angle is theta radians, then what is the length?
Beta r.
3R.
And the length there is just theta r. And so the length is just theta times your radius. As opposed to your length being theta times pi times r over 180. It's just your angle times your radius. Let's really quick see an example of this. I've got a circle here. We say it has a radius of 7 meters. And I say that I walk around the circle. This time I'm going to use radians. Pi third radians rather than 60 degrees. Question. How far in meters did I walk going from here to here? You just take 7 times that. 7 pi third meters. That's how far I went.
Yeah.
How trivial was that?
Degrees.
Easy as pie is what it is.
Oh.
And now, let's say that you knew theta instead of L. So I'm going to use this equation and solve for theta. So I know L is equal to theta times R, or in other words, theta is equal to L divided by R. So this time I say, actually, I give you that's the length I go. Find the angle. How do you find the angle? Divide by the radius. And you get, oh, then the angle is pi thirds.
Yeah.
This is why everyone uses radians. These conversions happen all the time the further you go in math. Going from talking about arc lengths to talking about angles, you go back and forth left and right. And this is even very closely tied to talking about waves. That doesn't make sense to you yet. You'll get some of that from Trig. How talking about angles and talking about waves are very closely related.
Yeah.
And once again, vastly superior. And it's because these conversions are so easy. Going from talking about arc length, talking about radians, to radiuses. How many radians is it? It's the same as how many radiuses if you're talking about the arc length. Same thing. That's why everyone does it.
Don't you normally learn radians and trig?
I don't know how normal it is to cover radians in geometry. I don't know what Mar geometry is, because it's not geometry.
Yeah.
So I don't know what it is you guys did at Masada that they slapped the geometry label on. But wasn't this. So I don't know what you guys have been up to. That's
Yeah, I hated.
How far into trig? Are we?
I
How
love
far into trig are we going?
I hate
In this course?
in this course. I would love to derive your basic trig identities that you would get a table of trig identities for. The two big ones being the sum of the angles and the difference of angles theorems for sine and cosine. And what falls out from those. Definitely your Pythagorean identities.
That's basically what we went through in calculus, but
Yes, basically trying to cover that same amount. Give you that foundation trig. So let's see. So I talked about a degree. we're going to skip theorem 12.9. It basically just talks about how you can use degrees to measure angles. Again, it's one that the author doesn't really prove. Just try to make you feel good about it. And we're also going to skip theorem 12.10, just like the author does, which is if two angles are congruent, then they have the same number of degrees. Now that one almost falls for free. If they're congruent, then they have the same arc length.
Yeah.
And degrees can be measured in terms of arc length. Right?
Yeah.
How do you get the degrees? You take the arc length, you multiply it by 180, and you divide it by pi r. Okay, so then he introduced the definition of a radian. We already did that. There were still some cool theorems I wanted to do. Oh yes, the inscribed angles. All right. What does he call the other one? Inscribed versus central angles. So cool theorem here. Kind of put a pin in this, and then we'll have a lot more to say about radians, get you comfortable with radians. But our last cool geometric theorem that I want to quickly prove. Our last cool geometric theorem is that if you have an angle, a central angle, here's my central angle, using O, and then I have any inscribed angle that uses the points A and B. What's an inscribed angle? It's an angle whose vertex lies on the circle. So I may draw a random inscribed angle using the points A and B still. So here's our central angle, here's our inscribed angle. You with me? We are going to prove that your central angle is always exactly double your inscribed angle. Not at all obvious. Pretty cool little theorem. You with me?
Yeah.
Okay, we're going to break this up into 3 cases. So the first case I'm going to handle is where the inscribed angle and the central angle both use a diameter of the circle. So it's, in other words, if I were to pick the point right there, so that 2 of their sides coincide. So let me draw that picture first. So here's the first case that we're going to handle. There's O. Here's A. Here's B. And now our inscribed angle uses the diameter. So our inscribed angle is this. So I'm trying to show out this angle is exactly half this angle. Or that one's twice as big as that one.
Yeah.
You with me? So I'm just going to start labeling. We'll call this one alpha. And I'm going to call this one beta. I'm trying to show beta is equal to 2 alpha, where alpha and beta are the measures of the angles. And now we can talk about in terms of degrees. Now we have degree or radians, whatever you're more comfortable with. Okay, now, what do you notice about this triangle over here?
Is it isosceles?
It's an isosceles triangle. And so what must this angle be? Yeah, so it must also be alpha, where alpha is the measure of the angles.
Right.
And what about this triangle over here?
Also isosceles.
Also isosceles. So whatever this angle is, I'll call that angle theta. Then this angle is also theta. I don't know why I drew that so high up. If this angle is theta, then this angle is also theta. Okay. Finally, look at this triangle. Let me call that the point C. Look at triangle ACB. What do we know about it?
Its measure is.
No, that's not isosceles.
You know its measure is a certain angle, or 30 degrees.
This is a straight angle. What kind of triangle is ACB? It's inscribed in a semicircle. It's a right triangle. Do you remember that proof?
Oh.
It's one of the coolest proofs. Take any triangle inscribed in a semicircle, and it's a right triangle. So alpha plus theta is equal to what?
The right angle.
So alpha plus theta is equal to,
Pi.
all right, we'll do 90 degrees instead of pi halves. Right?
Yeah. Correct.
So we know that fact.
How do we know that right angles are 90 degrees and straight angles are 180?
We'll take it for granted. But you could quickly get it, you can quickly get it from what portion of the circle it covers. So you plug 180 into that formula, and what are you going to get? Pi r, which we know is exactly half the circle. And so then you can say that those points all have to be collinear. And then half of that is going to exactly bisect the angle. And so you get two congruent angles, and so they're right angles. And so you can quickly make those arguments. Okay. So theta plus alpha is equal to 90 degrees. So what is 2 alpha plus 2 theta equal to?
Or sorry, 180.
180 degrees. You with me?
Yeah.
Now, let's look at this triangle over here. The one with beta, theta, theta. What do I know that beta plus, said it right. What do I know that beta plus 2 theta equals? Looking at this triangle.
180.
It equals 180 degrees. The angle sum of any triangle is 180 degrees, so this is 180 degrees. So 2 alpha plus 2 theta equals 180, and beta plus 2 theta equals 180.
2 alpha
Two alpha is
is equal to. Okay, yeah, I see.
So 2 alpha is equal to beta. You see it?
Yep. So alpha is exactly 1 half the beta.
So beta is twice as big as alpha. So we handled it, that special case.
Cool.
Good so far?
Yeah. What theorem was that?
I don't know.
Control
Theorem last.
More fast.
Yeah, last one in the chapter.
Okay.
Okay, so that was one special case where it happened to go straight through the diameter. Where it happened to go through the center of the circle. The inscribed angle went through the center of the circle. Now I'm going to handle the case where the center of the circle is in the interior of the inscribed angle. So now our picture is going to look like this. Here's my inscribed angle, or here's my central angle, I mean. Let me make it bigger. I think it will give me more space to draw. Our central angle, we'll say comes right here. Our central angle, that's our central, this is our inscribed angle. So now we're going to handle the case where one of the sides of the inscribed angle does not go through the center of the circle, but the center of the circle is in the interior. And then the last case we'll handle is where the center of the circle is exterior to the inscribed angle. Have to handle all three cases. You with me? Okay, so this angle, once again, we're calling alpha. And this angle, once again, wait, we did beta last time. Let's be consistent. Here's our beta, here's our alpha. I'm still trying to show beta is twice as big as alpha.
That does not look obvious.
Part of it could be my garbage picture, but.
It'll say twice.
So first thing I'm going to do, I'll redraw those things right there. The first thing I'm going to do is draw the line that goes through this point and this point. This point over here is our point C, right? Just label it. That's O. I'll write my O. I think I'm safe writing it right there. So I'm going to put a line that goes through these 2 points. An invisible line. With me?
Wait. Isn't that like the first one?
Now it's like the first case twice. This angle we'll call, we want the whole angle to be alpha. I'll call alpha sub 1 is this portion of the angle, and alpha sub 2 is that portion. You with me? So alpha sub 1 is this portion of the angle. And how does this portion of the angle, we'll call this beta sub 1. How does beta sub 1 compare to alpha sub 1?
Twice as big.
Is twice as big from the previous theorem. Because we've got an inscribed angle where one of its sides is the diameter of the circle.
Right.
And so it is exactly half as big as the central angle using the two same points. So I know that beta 1 is equal to double alpha 1. Similarly, call this angle right here alpha 2, this angle right here beta 2. And I know that beta 2 is equal to double alpha 2, same exact reasoning. It's an inscribed angle that uses a diameter.
Yeah.
With me? And beta 1 plus beta 2, that's exactly what we mean by beta. Beta is that whole angle, is equal to 2 times alpha 1 plus alpha 2. 2 of those plus 2 of those, factor out the 2. Alpha 1 plus alpha 2 is exactly what we meant by alpha.
Weird.
Good?
Yeah.
Okay. Now finally, we need to handle this case down here. With me? And we're going to do a similar idea, call this C. Similar idea, but this time I'm going to add my green line. Like that. So I know that this whole angle, do I have any other colors? Let's see if I can get, remember, okay, that up. So look at this red angle, and look at this purple angle. How do they compare? How does purple compare to red?
Red is twice the size of purple.
Red's twice as big. So I'm going to call red here our beta and purple our alpha. So I know that alpha is equal to 2 betas. Where beta's that whole thing and alpha's that whole thing. Right? Now I'll call just this little portion right here beta 1. And I'll call just this portion right here alpha 1. How does alpha 1 compare with beta 1?
It's not as big.
Right, once again, beta 1 is equal to 2 alpha 1. You with me?
That's your first or second.
And then this angle, the angle we started with, let's call that one alpha 2. And we'll call the remaining portion of beta over here beta 2. So I know that alpha is half beta. That's this, right? So I know that alpha 1 plus alpha 2 times 2 is equal to beta 1 plus beta 2. I swapped them. Sorry. Making a mess. Red is our beta. This is our alpha, right?
Oh, yeah.
Sorry. So alpha, our purple angle, is equal to, or 2 of that is equal to beta. 2 alphas gives us beta. 2 of our purple gives us our red. Okay. This is saying that same thing. 2 of our purples gives us our red. With me? But I know that beta 1 is equal to exactly 2 of alpha 1.
Yeah.
So let's distribute over here 2 alpha 1. 2 alpha 1 plus 2 alpha 2 is equal to beta 1, which is 2 alpha 1, plus beta 2. Subtract 2 alpha 1 from both sides, and I get that beta 2 is equal to 2 alpha 2. So this angle, beta 2, is equal to double alpha 2, which is what we were trying to show. So we did it where it went through the center. Then we did it where it contained the center, and that was just adding together 2 that went through the center. And then we did it where it didn't contain the center. That's just taking the one that does contain the center and subtracting off the smaller portion that didn't contain the center, showing the results are equal. So this one was kind of like they were equal. This one is equals added to equals or equals. This one is kind of using equals subtracted from equals or equals. See all that? Okay, so that was our last theorem. Now, let's go back to talking about radians and trying to get more comfortable with radians and introduce you to some basic trig.
Sweet.
And we're going to try and quickly fill out what we call a unit circle.
Do we have any more geometry after this?
You're saying in our textbook?
Yeah.
Yes. Yeah, we have a lot more geometry to cover still, don't worry. And you have a test next week.
Yeah.
So don't worry about that either until after class, and worry the rest of the week. Okay, in the meantime,
We're bringing notepads for that, right?
yes, you're allowed to use notes for your tests. You can even bring a calculator if you want. I'm just so kind. Okay, so let's talk about now the unit circle. If I can draw this, I can't go that close to the edge. I need some space. What am I doing? Try and draw it a bit smaller so that we have space, but you also want it kind of big so that you have enough space to draw everything. That is supposed to be a circle. We're drawing a circle centered at the origin, and it's a circle with radius 1. You with me? So maybe in red, try and quickly do the x-axis and the y-axis just to...
We haven't talked about coordinate systems yet.
Nope, we have not talked about analytic geometry yet. That will be one of our chapters. So this is not talking about trig anymore. Or talking about geometry anymore. This is briefly giving you some foundations in trig. And what we do in trig and what we talk about in trig. So it's a circle with radius 1. You with me?
Yeah.
So the coordinates of this point would be what?
On the top point, 0, 1.
It's 0 in the x direction, 1 in the y direction. You with me? What would the coordinates of this point be?
1, 0.
1 in the x direction, 0 in the y direction. Over here we would have negative 1 in the x direction, 0 in the y direction. Right? And then down here we would have
0, negative 1.
0 in the x direction, negative 1 in the y direction. You with me so far?
Yeah.
Now we're going to go around measuring the degrees and radians of each of these things. So let's look at going to here. How many degrees is it to go all the way back around to here?
360.
360 degrees, which is how many radians?
2 pi.
Get rid of that. 360 degrees, which is how many radians? 2 pi. All right. Now, Caleb, getting halfway around the circle, how many degrees is that? 180 degrees, or pi radians. Good. And for straight up, 90 degrees, or pi halves. Straight down, 0 degrees is right there. 270 degrees, or in radians,
3 pi halves.
3 pi halves. Pi halves, 2 pi halves, 3 pi halves. 4 pi halves, or in other words, 2 pi again. Right? Okay. Now let's try and get ourselves in trouble here. You have to rely on my artwork a lot. That was intended to be a 45-degree angle. How many radians is it? We'll draw it on top of the line. That might make more sense. So this is 45 degrees, or pi fourths. Good. Right? If this is pi halves, this is half of that, or pi fourths. Look, the way that you get these, the way that I get these, is I ask myself, what portion of the circle are we talking about?
Yeah.
This is 1/8 of the circle. What's 2 pi over 8?
Pi over 4.
Pi fourths. So I'm just always asking in my head, what portion of the circle is it? It's exactly what you did when you would calculate that's 45 degrees. You said, what's 1/8 of 360? And then you got used to the fact after time that that's 45 degrees, but when you were first getting comfortable with it, that's the way you thought about these things. All right, let's go and do 30 degrees here. So this is 30 degrees. 30 degrees is 1/12 of the circle, right?
Okay, so it's going to be
Pi 6. So 30 degrees, or pi 6. And what about if we went up here to 60 degrees? So this is 60 degrees. Or in other words, it's pi thirds. It's 1/6 the circle. 60 degrees, pi thirds, same thing. With me? Okay. Let's keep going with this. Over here at 120 degrees. Two pi thirds. It's just double what it was at 60 degrees. Right? So this is 2 pi thirds. Let's go over here to 150 degrees. 5 pi 6. Good. And over here at 135 degrees. 3 pi 4s. You with me? And we can keep filling these out. Should we do all the points?
Should.
All right, let's do all the points. Let's start marking them out here. Try and get somewhat decent. Do. Okay. Start telling me the degrees and the radians. Come on, 210 degrees. Now what's the radians?
7 pi 6.
7 pi 6. Okay. Come on. Beat me to it.
225.
225. Where was it in radians?
4 pi. 5 pi 4s.
5 pi 4s. Beat me to it. 4. How many 6 did we use? 1, 6, 2, 6, 3, 6, 4, 6 of the circle, right?
Yes.
So 4th 6 of it. We have 2 pi times 4/6. 2 pi times 4 is 8 pi over 6. 4/3 pi. All right, 4 pi thirds. Okay, we already did this one, right?
Yeah.
Coming over to here, what's our angle? Beat me to it. 300. Or in terms of radians, we added a 6 got us to there. Another 6 gets us. Oh, that's not 6, that's a 12, sorry.
So 6 to the 12.
Well,
No.
don't think about it that way. Let's think about what portion of the circle are we missing? We're missing 1/6. However you want to think about it. What portion of the circle is it?
5, 6.
5/6. So we multiply that by 5/6.
10,
10/6, which is
5 thirds.
5/3. So 5 pi thirds.
You're just adding thirds.
Over here, what's our angle? Come on, don't make me write it.
210. Wait.
352 each time.
Did I hear 52?
It said 350.
350? It's got to end in the 5.
She's saying 350.
15.
Oh, 315. Okay, thank you. That was my own hearing. You were right. 315 degrees, that is correct. Okay, and we got 7/8 of the circle.
7/4.
7/4. Just cut the denominator in half. 7
5/4.
pi 4s. And then finally the last one. In degrees, what is it?
230.
330 degrees. And in terms of radians, what is it?
11 pi 6.
What?
Is it?
I didn't hear you.
It's 11 pi 6.
11 pi 6, yes.
Because you're 1/6.
What portion of the circle do we have?
Oh,
11/12 times 2
Yeah, you're 1/6
is
away.
11/6.
You're 1/6 away from
11/6 pi. 11 pi 6. Yeah. So just forget the pi for a second. Take what portion of the circle and then multiply it by 2 pi.
Yeah.
So you got 11/12 times 2 is 11/6. Throw the pi out.
Are we doing the coordinates? Do we know?
Of course we're doing the coordinates.
Oh, sweet.
Of course, of course. Now we want to find the coordinates of each of these points. Which means we want to find out how high up it is and how far over it is. You with me? We're going to start out with this one at 45 degrees. So imagine I started at that one at 45 degrees and I dropped this perpendicular. So we got that right triangle to this point. I'm going to redraw that right triangle to help us think about it. So drawing that triangle, here she is. Where I know that this angle right here is 45 degrees.
We know the hypotenuse is 1.
How do I know that the hypotenuse is 1?
It's unit circle.
It's a unit circle. What is a unit circle? It's a circle whose radius is a unit. It's 1. So this is 1. What's this angle right here?
But
This is a 90-degree angle. It's pi 4 throwing you off. Okay, we'll call it 45 degrees.
it's going to be
45 degrees. There's a right angle. What's that? 45 degrees. Because the angle sum of a triangle is 180. Oh, were you saying it? You got to talk so I can hear. All right. Got to speak up loud so I can hear you. Okay, so there is our triangle.
Yeah.
Now, we are trying to find out the coordinates of this point, which is how far over and how far up it is. So the xy coordinate here, this is coordinates xy, we're trying to figure out what those are. The x here is how far over this way we go, and the y here is how far up we go.
Yeah.
You with me? Now, what kind of triangle is this? It's right, but it's also isosceles. So how does x compare with y?
It's the same.
They have to be the same distance.
Figure out, yeah.
So they're the same, so I'm just going to mark that as x, since however far over we go is how far up we go. You with me? Pythagorean theorem. X squared plus x squared is equal to 1 squared.
Which one?
That side squared plus that side squared is equal to that side squared, since it's a right triangle. X squared plus x squared is 2x squared. So 2x squared is equal to, what's 1 times 1? Ooh, that was quick. Okay, divide both sides by 2, and I get x squared is equal to 1/2. I'm trying to figure out what x is. What do I do next?
Square root of
Square root both sides. So x is equal to plus or minus the square root of
1/2.
1/2. Now the square root of 1/2 is the same thing as the square root of 1 over the square root of 2. And is our y going to be positive or negative?
Positive.
Positive. Our x is positive and our y is positive. So we have plus or minus here. Do we want the plus or the minus?
Positive.
Notice that if we were talking about the triangle that comes down here, we'd want our x positive but our y negative.
Right.
We're talking about the triangle up here, so they're both positive in this case. So we can ignore the plus or minus and just take the positive case. You with me?
Particular part of the coordinate.
Oh my goodness. Can I even see this unit circle on camera?
Yeah.
Everything except for my 1, 0. Okay. Okay. Next. Okay. So the square root of 1/2 is the same thing as the square root of 1 over the square root of 2. You with me?
Good.
So x is equal to the square root of 1 over the square root of 2. What's the square root of 1?
1.
1. So 1 over the square root of 2. Now, as a matter of convention, we do not like square roots in the denominator. Just a convention. So we're going to get rid of that in the denominator. How do I get rid of square root of 2 in the denominator?
Times by root 2 over root 2 over root 2.
Yeah, I've got to make sure I don't change my number. So if I take a number and I multiply it by 1, what happens to the number?
It's the same.
Nothing. So I'm going to multiply this number by 1, a very special one. Okay? What's the square root of 2 times the square root of 2?
It's 2.
2. That's what we mean by the square root of 2. What is the square root of 2? It's a number that when you multiply by itself, you get 2.
No.
What's the square root of 4? 2. How do you know? Because 2 times 2 is 4.
Yeah.
So square root of 2 times the square root of 2 is 2. 1 times the square root of 2 is the square root of 2. And that's the way we say it. And so our x coordinate here is the square root of 2 over 2. And the y coordinate is the exact same as the x coordinate. And so that's going to be,
Is the exact same because
It's isosceles.
it's isosceles. Oh,
because it was an isosceles triangle. Yes.
okay.
And so that's going to be 0.71251, whatever it is, when you do the numeric approximation. Notice it's going to be less than 1. It doesn't go 1 up. It goes a little bit less than 1, and it goes a little bit less than 1 over. Make sense?
Yep.
So we found the coordinates of that point. Let's look over now at this point right here.
It would be negative root 2 over 2. Root 2 over 2.
Notice that if we drop down this right angle, this triangle is the exact same as this triangle. They're congruent to each other. It's just flipped over here.
Yeah.
And so it goes up just as much as this one goes up, and it goes over just as much as this one goes over. It just goes over in the opposite direction.
So it's negative root 2 over 2.
Right, so its x-coordinate is negative root 2 over 2, but its y-coordinate is the exact same.
Yeah.
With me? Okay, so we did those 2 points. Let's come and do this point really quick. Actually, we're going to do this point. Let's do this one next.
Okay.
This one right here. This is the one that's at 60 degrees. So if I drop down this line, that's going to be the triangle that we're talking about. You with me?
Yep.
I'm going to come scribble that triangle over here. We'll start down here. And that purple line that I dropped it down so it was perpendicular. So that's a right angle in how I dropped the purple down.
Yeah.
What is this angle right here?
60.
60 degrees. What is this angle right here?
30 degrees.
30 degrees. How did she know that? Because they have to sum up to 180. So she did 180 minus 90 is 90, minus 60 is 30, so that one has to be 30. Okay. So that is that triangle. We are looking to figure out how far over it goes and how far up it goes.
Yep.
That's the same thing as trying to find this x and this y. You with me?
Yes.
Now I am going to construct a triangle congruent to this one right next to it. Before we do that, let's mark one more value. What is the distance from here to here?
1.
It's 1. How do we know that?
It's the radius of the circle.
It's a unit circle, and that's the radius of the circle. So that's 1. Okay, so now I'm going to construct a circle, a triangle, congruent to this one flipped over here. So, try not to be too sloppy with my drawing, but not going to be perfect. So that's a right angle, this is 60 degrees, and this right here is 30 degrees. With me?
On that side of that one.
Now, this angle is, this angle is,
60 degrees.
and this angle is.
60 degrees.
So this triangle, the exterior one there, is called
Equilateral.
an equal angular triangle.
Which we-
And equal angular triangles are also equilateral. So what is the distance from here to here?
1.
1. And what is the distance from here to here?
2x or 1.
1. Because it has to be the same as that distance because it's an equilateral triangle.
Right.
So x is half of that. So what is x equal to?
1.
So we know that x is equal to 1/2. You with me so far? So over here, the coordinates of this point so far, we know that the x is 1/2. We don't know the y yet, but the x is 1/2. So we went over, if this is 1, we went 1/2 over if I would have drawn a completely accurate picture.
Which makes sense.
Should make sense so far, yeah. Okay, now we gotta figure out the y. You You with me? So let's redraw this triangle now. But we now know our x. So I've got this triangle. Here's my y. X I now know is 1/2, and this is still 1.
Yep. Well, let's put that in here.
Right, Pythagorean theorem says that squared plus that squared equals that squared. So I know that 1/2 squared plus y squared is equal to 1 squared. What's a half times a half?
1/4.
1/4. So I know that 1/4 plus y squared is equal to 1 times 1 is 1. Subtract 1/4 from both sides, and I get that y squared is equal to, what's 1 minus 1/4? 3/4. And now y is equal to the square root of that. The square root of the whole thing is the same thing as the square root of the top over the square root of the bottom. And we're going to take the positive because we know our y is positive in this case. And what's the square root of 4? 2. So this is equal to the square root of 3 over 2.
That's the right. Is it
Oh, that's what I'm saying. So this is root 3 over 2. And root 3 over 2, what is that approximately? I don't know, 0.826, whatever it is. Some approximate number. It's going to be close to 1, but not going to be 1.
0.8866.
0.866. Okay, so that's the coordinates of that point. What about the coordinates of this point now? Notice that the triangle we get when we drop here, if I drop this line down, so we're talking about this triangle, right?
Yeah.
What angle was this triangle making?
30 degrees.
30 degrees. So let's draw it over here really quick. That's this angle, this triangle. That's terrible. Trying to do something more 30 degrees looking. This was 30 degrees. This was 90 degrees. What's this angle then?
60 degrees.
60 degrees. So notice that this triangle and this triangle are the exact same thing with the x and the y flipped. So if this one was over 1/2 and up root 3 over 2, this one is going to be over
Root 3 over 2.
root 3 over 2, and it's going to go up
1/2.
1/2 for the exact same reason, same argument. You with me?
Yeah.
And again, you can reflect those points over here. And so this is the same height as that, and it goes over the same part just in the negative direction. So this is minus 1/2 and root 3 over 2. This one is minus root 3 over 2 and 1/2. And now you can take all these points and reflect them downwards, and it just makes all the y's negative now. Right?
Yeah.
So the coordinates of this point are, make sure we don't think it's part of that, negative root 3 over 2 and negative 1/2. Just same exact x, make the y negative.
Yep.
For this one, negative root 2 over 2 and negative root 2 over 2. Just following that point, right?
Yep.
And for that top one up there,
Negative.
minus 1/2 minus root 3 over 2. Come over here, 1/2 minus root 3 over 2. This one is root 2 over 2 minus root 2 over 2. And this one is root 3 over 2 and minus 1/2. All right. So you'll notice if you look in the back of the classroom, that unit circle that all the trig students love, that's exactly what this thing is. And this is what they talk about with the unit circle. And it has all those numbers, and that's what all those numbers on there mean. It's talking about the coordinates, and it shows you the angle in degrees, it shows you the angle in radians, and it shows you the coordinates. You just did that. Let you guys know, right now you're looking at your last test in the class. Your last test in the class, I'll give you a blank unit circle and you will fill it out. So you're going to want to memorize this thing.
What about our trig identities? We're taking tests on that?
Huh?
Taking these tests on our trig identities?
No. But, so this will be clear at the last of the class, so you don't need to worry about it yet, but just letting you know, here's your last test. It will be fill out that unit circle. And it's a gimme
Is it time?
to boost all your grades up. Yeah, you have 2 minutes.
2 minutes to
Yeah, because you need to have it memorized.
Bro, I did it.
This isn't refigure it out over the course of an hour. It's did you memorize your unit circle? Because you're going to use this thing left and right when you get to trig, when you get to calculus, when you get to physics. This thing never goes away.
Yeah.
All right. Now, going to teach you to understand some fancy trig language now. I'm going to introduce the backbone of trig, which is 2 trigonometric functions, sine and cosine.
We're doing a lot of trig.
Well, we're just doing the unit circle and sine and cosine.
Right.
There's 4 basic definitions that you want to make sure you understand when you go into trig. The 4 basic definitions are the definition of pi. What's pi? Circumference over diameter. The next definition that you need to have nailed down is the definition of a radian. What's a radian? It's an angle whose arc length is 1 radius. The other 2 definitions that you need to have down are the definition of sine and cosine. These are functions. So, starting out with cosine. COS for cosine. It's a function. And it takes as an input some angle. And it spits out an x-coordinate on the unit circle. Sine takes as an input some angle, and it spits out a y-coordinate on the unit circle. So when you get to trig, you work with these functions, and you watch trig students calculate these functions. They only know how to calculate these functions for very special values, and it's the values that show up on the unit circles, or values you can get to show up in terms of these values. So let's try this out and get a feel for it. If I ask you for what is the cosine now of 30 degrees? Cosine is a function. It takes an angle and it spits out the x-coordinate on the unit circle at that angle. What is the x-coordinate at 30 degrees on the unit circle?
One. Yeah.
Root 3 over 2. Similarly, you might have seen something that looks like this. What is the cosine now at pi halves? That is now radians.
0.
Zero.
So we go over here to pi halves. What's the x-coordinate at pi halves? 0. Let's try another one. Let's start alternating. You answer, then you, then you, then you, then you, then you, then you, and repeat. I'm just going to write a bunch of problems up here, and you're going to tell me what the answer is. Let's clear some space. All right, so let's start with cosine of 5 pi 6.
Zero.
It is negative root 3 over 2.
So we're looking for the negative x-coordinate, or sorry, we're looking for the x-coordinate on the unit circle at the angle 5 pi over 6. And so the x-coordinate is negative root 3 over 2. Next, give me the sine of 3 pi halves. So we're looking for the y-coordinate at this angle.
Y coordinate is negative root 3 over 2.
Negative 1 at 3 pi halves, which is 270 degrees. Okay, so 3 pi halves, that's the same as 270 degrees, that's straight down. The y-coordinate there, just negative 1. Okay, let's try another one. Let's try the cosine at 2 pi.
That'll be
1. The x-coordinate at 2 pi, or 360 degrees, is just 1. All right, let's try cosine at 45 degrees. So now we're doing degrees instead of radians. 2.
It'd be above like 0, right?
No, what's our angle? 45 degrees. What's the x coordinate at 45 degrees?
2 over 2.
Root 2 over 2.
Yeah.
Good. All right, let's try another one. Let's look at sine at 135 degrees.
Sine?
Yep,
Root 2 over 2.
root 2 over 2 again. Okay, let's look at the cosine at negative pi halves. Let's get tricky. Yeah, that one doesn't really show up there. If I have an angle of pi halves, that's right here.
Okay. So you're looking for the cosine 0?
So at negative pi halves, that's down pi halves, and the answer is 0. All right, let's try this one. Let's look at the sine at negative 90 degrees.
Would that be negative 1?
Just negative 1. Same thing. All right, let's get a bit trickier. Let's do cosine at 1,596 pi.
That's negative, is that negative 1 or 1?
Has to be one of them.
I think, I can't remember which one.
You're trying to memorize it rather than thinking about it.
You gave me a formula for.
Yeah, stop trying to remember a formula, just think about it.
It's negative
1. You guess.
I didn't guess, kind of.
0 pi gets us here. 1 pi gets us here.
Oh,
2 pi gets us here.
yeah.
3 pi gets us here. 4 pi gets us here. 5, 6, 7, 8, 9, 10. Right?
So it's just.
Is this an even number or an odd number? Even. So it's going to end right here. It's some multiple of 2 pi. Right?
Okay, that's cool.
Let's try the other one. Let's talk about the sine at 1,76251 pi.
Negative 1, sorry.
The sine, not the cosine, the y coordinate. What's the y coordinate right here? How high up are we?
0.
0. The y coordinate. So 0 pi, we're right here. At 1 pi, we're still up 0. At 2 pi, we're still up 0. At 3 pi, we're still up 0. So anytime it's a multiple of pi, your sine instantly comes out 0. You don't even have to think about even or odd.
Oh, good. Oh, that's cool.
Make sense?
Yeah.
Because every pi is counting half a circle. Anytime you go half a circle, in terms of height, you're back where you started. All right. One more tricky one. 2 more tricky ones. 2 more tricky ones. So here's one more tricky one. Now let's look at the sine of, we'll keep it smaller, 13 pi halves.
Okay. Would it be 1 or negative?
It's got to be one of the two, right? Because it's some multiple of pi halves. This is the same thing as sine of 13 of these pi half things. Now, if you're at a complete loss, you can always just count 1 pi half, 2 pi halves, 3 pi halves, 4 pi halves, and do it that way. Or you can try to think, how many halves gets me all the way around the circle?
It's 1, right?
How many halves gets me all the way around the circle?
2.
Sorry, how many pi halves?
Yeah.
So we have 13 pi halves. Yeah, I was saying about how many pi halves? So here's 1 pi half, 2 pi halves, 3 pi halves, 4 pi halves, and we're back to where we started.
So 4.
So we can get rid of multiples of 4. So this is the same thing as,
Minus 12, and then it'd be 1/2. Or-
perfect. So this is the same thing as 12 pi halves plus just 1 pi half. So those 12 pi halves just gets us back where we started. And then one more gets us back to the top, which gets us the 1.
Yeah.
Okay, last tricky one. What is the cosine at 197,625 over 2 pi?
Oh.
So whatever this is, it either has to end at the top or the bottom of the circle. Has to be one of those two. And we're looking for the x-coordinate. What's the x-coordinate at the top?
0.
No, 0. What's the x-coordinate at the bottom?
0.
So we don't care which of those 2 points it is. In either case, it comes out 0. Good? Okay. So there you go. You've done some basic trig calculations with some basic trig functions. Make sense? And the way these functions are defined all just comes from this unit circle.
Can't you also define them in terms of triangles?
You can. It's logically equivalent. But I like to introduce the unit circle and then define it in terms of the unit circle. I think that's the most straightforward way to see it, rather than introducing it. Now, just for the sake of completeness, I'm going to give you the other 4 trig functions, and then these are all the functions you work with in trig. We won't bother doing many calculations with them, but just for the sake of completeness, so that you see them all.
We know what
These are the 2 basic ones that you need to know. Everything else comes from those. So there's what's called the tangent function, tangent of theta, and it is by definition just sine of theta over cosine of theta.
Have we talked about what a function is in this class?
We're not going to give a precise definition of the function. We were going to do that when we talked about limits, but we didn't have time to do that. So if you know how to calculate sine of theta and you know how to calculate cosine of theta, then you know how to calculate tangent of theta. You can just figure it out, whatever it is. Let's just quickly do one to help us get comfortable with it. Let's look at tangent of root 2, or sorry, spitting out the answer, of pi fourths. That's going to be sine of pi fourths over cosine of pi fourths. That's what it is by definition. Our y-coordinate at pi fourths is root 2 over 2, same as our x-coordinate. So this is root 2 over 2, all over root 2 over 2. What's a number divided by itself? 1. Intuitively, what the tangent gives us is the slope. What's the slope of a 45-degree line? 1. The rise over run is 1. That's intuitively what it gives us. But you see, if you know how to calculate sine and cosine, you can always calculate tangent. And then you have what we call the secant function, secant of theta. By definition, it's just 1 over cosine of theta. So if you can calculate cosine, flip the reciprocal, that gives you secant.
And you never do cosine over sine. Okay.
No.
We do.
We'll get it.
The next one is cosecant of theta. This is just defined to be 1 over sine of theta. And then finally, we get cotangent of theta. And this one is cosine over sine of theta.
Which is the same thing as 1 over tangent.
So it's run over rise.
Run over rise, rather than rise over run.
Okay.
Does that give you anything intuitively? Geometry.
One of the ways it can, where these names all come from, there's a reason that they're all named the way that they are. And there is a construction that accompanies them that makes their names make sense.
I see.
But you see that all the other trig functions, tangent, secant, cosecant, and cotangent, they're all just defined in terms of sine and cosine, sine and cosine, sine and cosine.
Yeah.
So if you understand sine and cosine, then you can figure out what all these other functions are. Now there's more insight to get from these functions, and when we do our trig lecture, we will go deeper into some of these relationships, introducing them to you now. But the 4 basic definitions you need to understand trig. Give it to you again. The definition of pi. What's that? Circumference over diameter. The definition of radian. It's the angle whose arc length is 1 radius. Definition of cosine. It's the x-coordinate of an angle on the unit circle. Definition of sine. It's the y-coordinate of a point, the y-coordinate of an angle on the unit circle. Thank you. All right, so that gives you our basic taste of trig so far, the unit circle, and that finishes chapter 12. None of this trig stuff will show up on your test. The chapter technically ended with the proofs we did right here. All this, that was just bonus, just for you guys. You're so lucky. So that's it for chapter 12. We're going to have our test next week, our test 3 next week,
What do we have?
on chapters 9 through 12, I think.
Yes.
And then this is the end of like the hard stuff. Things just get so much easier from here.
Sweet. Do we ever practice test?
Yes, I've got a practice test for you. Any questions that you want recorded before we end lecture? Okay. Yeah, we can start quickly going over this